Okay, I think we'll get started. So good afternoon, everyone, and welcome to our June Coding Club session. So we're going to kick off today with, this is our session outline. So everything today is about the shiny and new, relatively new, Baskerville. So we have Gavin here from the Bear team and Simon Hartley, and they're both going to be talking to you today about, particularly about GPUs and the sort of shiny, exciting kit that Baskerville offers for all of you as users. We will have time for some Q&A, so if you do have questions, whether you're online or in the audience, then do hang on to those, and after each talk we'll have time for some questions. So we're happy to hear from you for those. And I'll just give you a quick update on our next session at the end of the talks. So I shall now hand over to Gavin.
Can everybody hear me?
Yes.
What I'm going to be talking about today is Baskerville's GPUs for you, GPUs for me. And this slide is just about how to get access to Baskerville and some of the things we've done in Baskerville over the past year. I'll do a very quick overview of some of the kit we have at Baskerville, or what we have at Baskerville, and go through some testimonials and just the importance of GPUs. First thing I want us to say is why Baskerville, why that name? It was named after John Baskerville, who was an industrialist, and it is an EPRC funded tier 2 HPC system. And if you know the layout of HPCs, here at Birmingham, we have a tier 3 HPC system called Blue Bear, and tier 2 is a Baskerville one, which has a much broader reach around the country. So we've got a few consortium partners who are listed there, from the Rosalind Franklin Institute, Diamond Light Source, and the Alan Turing Institute. And we have a few technological partners, including NVIDIA, Lenovo, and OCF. They all helped come together and helped, I guess, build Baskerville for everyone to use. And why GPUs? Why are GPUs so important or becoming so vital in the research landscape? Well, one quote says that today's researchers can take advantage of GPUs to approach computational models and models for drug discovery and designs that are accurate, affordable, and achievable. With adequate computational resources, it is now possible to optimize a lead in days or weeks, and weeks instead of months. GPUs can make things a lot faster and enable you to get your results and a lot quicker, and able to analyze them and produce this high-level science and get high-level research and get it out there as fast as possible. There is a great adoption of GPUs in a lot more traditionally CPU-focused applications, with additional resources to enable upscaling of non-GPU accelerated code. The resources are there to help users and everyone out there who wish to use GPUs to do so, and we've spoken about a lot more in the next speech. One quick analysis on GPU's performance is an idea of speed. And NVIDIA did a quick test to see how many CPU nodes can be replaced by a single GPU server. And they created something called the, just trying to move this out the way. They created a kind of factor to relate this to show how many CPUs are equivalent to a single GPU server for a series of traditional applications. So I've got a few molecular dynamics applications here: AMBER, GROMACS, LAMMPS, NAMD, rely on, and showcasing that this is how many CPU nodes are equivalent to a single GPU A100 server. And again, for Quantum Espresso down there at the bottom, you can see it shows great performance compared to traditional CPUs. And with all that talk about GPUs, what does Baskerville contain? Here's a list of the specifications which we have at Baskerville, and showcasing just how GPU intensive it is and focused, including each node having the 4 NVIDIA A100 40GB GPUs and the 5+ petabytes of storage. I will say that we are constantly upgrading Baskerville. So we have the 40GB GPUs, but we are also in the process of installing some 80GB GPUs for people if they ever get to utilize that sort of memory. How do you access Baskerville? Now, with Baskerville, we're doing 6-month substantial projects here at Birmingham, and there's the website that you have to click on to apply. Such questions you'll be asked about is the area of research that you're doing, this type of software applications that you use in your research, and also what type of jobs you're going to be using. Are you using single GPU, multi-GPU, multi-nodal, multi-GPU type of work? And this can best help us understand what your research needs are. With Baskerville, we try to encourage people to use Baskerville. We have a lot of resources available for people. And these are some of the websites we have. The main public facing website, we put news and just general information on what Baskerville is. The admin website, once you've gotten a Baskerville account, you can look at this to see the projects you're on, and also some of the resources you've been using, such as the jobs you've submitted, how long they've lasted, and you can just gain an idea of what sort of work you've been using on Baskerville. There's the Baskerville Apps website, which gives a list of applications on Baskerville. And we also have Baskerville Portal, which can be used for GUI apps and also have access to Jupyter notebooks. I will be going through some of these websites in a bit more detail later on. Now, one website is the docs.baskerville website. This is a key information website. If you're using it, it'll be used to answer any initial questions you might have. Even if you don't have access to Baskerville or interested in GPUs or Baskerville setup, I do recommend looking at this website. It contains a wealth of information about Baskerville. And we even have a small teaching session in that website called Baskerville Basics. And it's just an introduction to Baskerville. And even though it's a tier 2 HPC system and a lot of people do have experience with HPCs, it's still valuable experience just to know that not each HPC system is the same. There's some slight differences in how they operate. And if you look at the Baskerville Basics, it can get you in line with what we expect with users in Baskerville. Some of the key features that you will see and try to accomplish when covering that course is how to access Baskerville, the apps website, how do you load modules on Baskerville and different environments, using Slurm, commands such as sbatch, sq, scancel, building a submission script and obtaining CUDA code, operating it with a range of GPUs, and methods of file transfer when you've got all your information using SCP and rsync. This is just to get everyone used to how to use Baskerville, and whenever you have questions, this can be your first point of call, and then coming to the Baskerville team to help answer your questions. This is the Baskerville applications website. If you're familiar with Bear, it is a very similar website. We currently have 282 applications, or we did last week when I got this image. And we will constantly, or upon request, install any applications that you would like. With Baskerville, we do also enable your independence. So if you are a user who likes to have your own local applications installed, we are happy for you to do so and look at and help you out with that if you have any questions with that. And now Baskerville is almost a year old now, or over a year old. And here's some testimonials that we've gotten from a few people. So the first testimony we have is from Professor Matthew Folks. He is from Imperial, and he got it via the EPSRC Access to HPC core. And his quote is saying that access to Baskerville led to a supercharge of a code and developmental process. The powerful GPUs allowed us to carry out highly accurate quantum Monte Carlo calculations of large-scale particle systems, which famously require both large memory and high precision. The large number of GPUs and good interconnect also allowed us to implement and test multi-node MPI version of our code, allowing us to study much larger systems than would have been possible on a single node. And I've put in bold the main selling point from what the testimony said, and it says, to our knowledge, the work we have carried out using Baskerville would not have been possible using any other facility available in the UK. And one of his PhD students provided us with that testimonial. And so this is what we want with Baskerville for you to be able to do is utilize things that you might not be able to do anywhere else. And here's a couple of other testimonials. And the first one is from the Asimov group. They are a group mixed between University of Birmingham and with certain researchers in Warwick, but is a Birmingham-based project. And the testimonial goes through some of the ideas of the research. So the group as its own is a EPSRC Prosperity Partnership and has been granted allocation to Baskerville and access to feasibly running production-grade industrial computational fluid dynamics. And thanks to the DSL-based development approach, a number of optimizations and performance benchmarks in Baskerville, we estimate that a complex coupled with unsteady simulations, production-grade aero engine compressors consisting of 10 blades, rows. And I bolded out this, the grasp this kind of scale of what they're doing. 5 billion nodes with complete a full revolution in 8 hours, a simulation that will currently take a similar sized classical CPU cluster several days. So we are using Baskerville, you're cutting that time and you're getting that research done. And a final one is from one of our consortium partners, the Rosalind Franklin Institute, and that the Baskerville documentation has been very useful and serves as a robust starting point for our users. Thereupon their account creation, this has largely been sufficient to get users logged in for the first time on their own and lowering our support burden. We tend to support users to help them set it up, and it seems to be very intuitive that a lot of users find it quite easy to get access to Baskerville. And that can also help within certain groups where they sometimes spend a lot of time getting their users accustomed to new HPC facilities. And the main focus for the RFIs is help empowering our science users. And my last slide, I'll end with some of the things which we're trying to do with Baskerville and just events and outreach, which we've done or have accomplished. We've done things such as a touring data study group. We've had 2 of those so far. And this is where we get external, I guess, research institutions / some companies to come in and with problems, and they get users sometimes from different areas of the school who apply for it to work on Baskerville to do this sort of work, to do some work utilizing the GPU facilities. We also did something called an NVIDIA hackathon, which is a very similar thing where there was a series of problems and a bunch of users get access to Baskerville for a short amount of time and utilizing its GPU resources for it. There are the bear drop-in sessions where we've recently started sending someone familiar with Baskerville in person to a couple of those events to try and get people informed about Baskerville and what is available. And we're doing the Bear Challenge, which this year will be hosted on Baskerville for anyone who is taking part in that. And there's a series of lots of training courses and educational materials available for everyone. And this was kind of a very quick overview of Baskerville. I know the next talk is going to go into a lot more detail on GPUs, but I'll leave it there. And if anyone has any questions or points, please let me know. Thank you.
Any questions for Gavin before we do a swap over to Simon?
Got 2 questions.
Oh, I'll give you that so we can actually hear the question.
Hi, Gavin. That was really, really interesting. Lots of information. Can I ask a very basic question? And that's GPU. I'm used to thinking of these as, things that accelerate the graphics of an application. So should I be really thinking these more in terms of parallelized compute nodes? Because you did a lot of stuff in your talk about, accelerating applications that don't sound particularly graphical.
Thank you for that question. And yes, it is very heavily on these accelerating applications. I will say that the next speech will definitely go into a lot more detail, so I don't want to try to go into too much there. But I'm not to put Simon in the fire. He knows, I've seen his presentation. It's going to go into a lot of the applications and what you can accomplish using the GPUs. Next question.
Thanks, Gavin, and thank you for your talk. Just had a general question out of interest from some of the results that you showed at the beginning of your presentation, the tests that NVIDIA did on the molecular dynamics packages. Did they natively have sort of GPU, you could enable GPU computation on those packages? Or would you have had to refactor the code somehow yourself? Because these packages are quite big, aren't they? Is there support from other maintainers to do that?
Thank you for that question. I'm not sure about all of them, but I know that a lot of these codes have started to enable GPU capabilities in them. So I know GROMEX has it and LAMPS has it. So I assume, and so does Quantum Espresso, I assume all of these codes have had GPU capabilities enabled in them. They do a lot of tests with companies like NVIDIA, and they see the benefit of these, and then they want to start enabling these capabilities of software to get people to utilize them to the fullest and get these bigger and better simulations going.
Right, thank you very much, Gavin. We shall now hand over to Simon.
Hello, I hope you all can hear me. Good, good. My name is Simon Hartley. I'm a research software engineer in Half Performance Computing Systems, and I do bits of work on Baskerville. And today I'm going to talk about Baskerville, a whole lot of GPUs, what they're good for. And I've done lots of programming for GPU, and I'm going to explain some of the projects I've done at Birmingham in different departments, helping different people using GPUs. We're a coding club, so I'm going to focus first on CUDA, but that's not what I'm going to finish up with. I'm going to go into the other projects. So I will advance to the next slide. So how many GPUs? If you go to the, Gavin provided the website for Baskerville. If you go to Baskerville website, there's 184 GPUs waiting for you to play with. Shiny toy, I love it. The other day I went and it actually tells you how much utilization. So what we're doing here is trying to get you to use this more. Put that up to 90, we'd be really happy. Use it as much as you can. That's what it's here for, the T2 system. And I'm going to show you things that I have done on systems, on Bear and on Baskerville. So for me, GPUs are very good, but shiny new processors as well. Intel new shiny processors. This is from the Xeon webpage, and you can see it's a marketing thing. So it has max turbo frequency of 3.5 gigahertz, ultra path interconnect. So the GPU is behind this. So there's a very parallel processor there. And we allow you to submit jobs via Slurm. You get a core on this, or you get the entire node, and you can run your code in parallel or in single threaded if you want. But that's what it looks like. And we're all used to seeing GPU pictures, CPU pictures now. You have a core, and this is the Intel core. You can see 28 cores or 36 cores for the Intel Xeon processors. It has interconnects to the rest of the system. It has the ultrapath interconnect that goes to other processors, because there's 2 Xeon processors in that node. So there's a connect to another core just like this one. And then there is the PCIe 4 Gen 4 connections that go to the graphics cards. And there's graphics cards connected to each one of these. So an advantage of this processor, we're all used to programming. We have a number, which is a float, and it fits in the 32-bit registers. You can have 32 bits ints for whole numbers, or you can have 32-bit floats, and that's one clock cycle, one register. It puts it into memory, it does addition, it does multiplication, it does it for you. Xenon processor has this new AVX512, so it can do 32 floats at once. So that's basically an entire matrix multiplication transferred into the registers on the processor. So that's really fast. This is as fast as you can get. Putting things on registers is where the computer does all its work. Behind the scenes, when you compile things, this is what it does. It says, move that to there. This is how big that number is. This is how much each bit represents. And when you look, Bear itself, massively out of date, 2 whole years. It's like Cascade Lake 4 years ago. But now we've got these shiny new Ice Lake processors, terabyte of RAM and GPUs. So this is what we're trying to use and utilize. If you go to the NVIDIA webpage, NVIDIA makes the GPUs, the A100s, and it has teraflops. It talks about teraflops of how fast these can compute. It moves the data around. So it also has different cores, and I'll get into that in programming. So the different cores are focused on different things. It has floating point registers, so it does these floating point numbers, but it also has the integer registers. It has half floating point numbers, which are these brain floats. The brain float 16 and they're used for neural networks. So these brain float tensor cores that are on the A100s are used for neural networks, and I'll get into neural networks next. So it has, I just have to say, because I'm amazed by some of this engineering, you've got to just geek out about 54 billion transistors on that little key. It's like, what? You know, this is a massive amount of engineering. You've got to be impressed. You know. So I just had to do that. And when you look at it, this is a block diagram of the core. When you look at it, you get all these cores inside for parallel processing. So similar to the CPU, this GPU is for parallel processing. It has the PCI interconnect at the top, and it has what an NVLink, what they call an NVLink, which connects to other graphics cards. So processors talk to each other, graphics cards talk to each other, and talks to the CPU. So we have this PCI Express 4 coming in at the top, and we have NVLink going out to the graphics cards. So we can basically double our number of graphics cards we use, or even use 4 graphics cards, and connect passing data between the memory and graphics cards. And we're allowed to do that through the CUDA standard, treat it as one in terms of a unified memory processing. So as mentioned, we accelerate the applications by using these massive cores. We've got thousands of cores there in the A100s, and we can utilize these. So this is what the basic unit, if we think of a core in a PC, in computer graphics terms or compute processing terms, the streaming multiprocessor is the most basic unit. You get one multiprocessor. Inside that, it contains a couple of tensor cores, it has the floating point units, it has those, but this is the basic unit for compute programming. And when I started, they weren't called tensor cores, they were called raster operation units, ROUs, and you had to do real-time programming and adapt it to physics, which is what I started out at. So I've been doing this a while. So the first book I read was GPU Programming Gems, and they didn't even talk about this general purpose computing. They talked about real-time graphics, because this is what they were based for. These parallel graphics, a graphics system is parallel because the problem is very parallel. If you think about a screen, it doesn't depend on other parts of the screen, it only depends. So it's a parallel problem. It's massively parallel. And then they realized other problems are massively parallel. These texture operations are matrix multiplications. These loading of images are a matrix multiplication. And that's where I came in. So how would you do this? How would you begin? So if you're thinking about doing programming, we're in Coding Club. So let's start thinking about using CUDA. And the standard workflow is this, where we initialize our variables, the CPU does some work, and then we check that it works. The next stage is how we utilize GPUs. What we now do is in CUDA, we can access the GPU, so initialize it, and we have the memory on the GPU. It automatically gets transferred from the CPU to the GPU, where the GPU does parallel tasks. At the same time, the CPU can still do tasks, and it's still plodding through. Then we call a barrier to synchronize our work, and then we verify that that works. So similar workflow, but we've just offloaded lots of the computation onto the GPU to be done in parallel. So if your problem is parallel and doesn't wait for other parts of your code, these GPUs are perfect. You know, some matrix multiplications that are perfect for us. It's a parallel problem, doesn't depend on anything else, and you can think about using it. And so I did. I was like, yay, new toy, gonna go play. So I started playing, and then I had a problem, which was point clouds. I started looking at point clouds, finding shapes in point clouds. And I had my algorithm, I set it up, I programmed really fast. It went in C, it was quite fast. I was like, I'm gonna use GPUs. And I found lots of different candidate shapes. However, it was dog slow, because no matter how good it is or how parallel your problem is, your algorithm has to come first. The first thing you need to do is program your algorithm. First thing I did was I started with a box and then subdivided it, which sounds a logical way because subdivision could be a complex task. However, most of my computation was actually done in matrix multiplication. So my smallest calculation unit was actually taking up the time. I was wasting time on units that had sparse matrix and didn't actually affect the end result. So I'd have been better off going from bottom, which is dividing everything into my smallest units and then merging them into my largest units. So if you're doing this, first thing is get your algorithm, then start optimizing. And that's where my problem was. And I did it for point clouds, and I've done it for DICOM images and voxels on DICOM images for radiotherapy systems. Earlier, we were talking about using Baskerville in terms of its hidden optimizations, because languages now can use the graphics cards if they're there. We'll have libraries. Intel threading library's been around for a while, and now they're introducing one API. CUDA's been around. Cycle is now the open source, a growing open source standard for this, these libraries. So we're seeing more and more languages have this built in by default. There'll be a CUDA version or CUDA library that has been optimized. So it'll just pick up the fact that if you run MATLAB or run Python, you can actually just pick up sometimes automatically that the matrix multiplications in there are already optimized. And obviously, as Gavin mentioned earlier, the standard applications for HPC are already optimized. GROMACS, LAMPS, AMBER are already optimized. I'm here to talk about neural networks. I'm not going to explain a neural network. We're all intelligent people who've heard about it for decades now. It's inspired by what we think of the brain, and we have layers, and we can think of it as matrix multiplication. And I've been involved in a project and in the medical school, and what it was related to was natural language processing, which is the ability of computers to understand speech and text, and context is a big thing. So in 2018, Google released its BERT model, which was a massive model. And this is part of the race to conversational AI. Google released BERT, which is trained on very large data sets. There's 2,500 Wikipedia articles were scanned, thousands and hundreds of millions of books. So it was trained on a very large data set to produce this neural network that outputs. So BERT itself is a bidirectional encoder representation transformers, and we can explain those terms to you if you want, or if you want to just use BERT and specialize it for your system. I have helped people in medical school train specific versions of BERT. So what we can think of is, as we had matrix multiplication, we can tokenize a sentence, and we can work out from the token embedding what the context is. BERT was unique in that it had this type of, instead of left to right organization, it had a bidirectional formatting that gave you the context of the words. So this is the matrix operation, how you'd set it up. And the way you use, or most people use BERT now, is you have BERT, the pre-trained model, which has a whole set of weights for the neural network, which is, how much this can affect the neuron effects of the neurons. And then you fine tune that on a new corpus to give you, and you're using the training that already exists to give you specialized results. So this is what people do, and I've introduced people using Word2Vec or Doc2Vec before this, and now people are using BERT to do this type of fine tuning of BERT to give a specific thing. So large inference and training is what it's for. This 40 gigabytes, BERT was a big model. When I first tried loading this on a P100 BERT, it actually failed completely. It needs at least 16 gigabytes of memory for the full BERT model to do. So this is why Baskerville is basically built for things like BERT. It's a very large model, very large data sets. And what we are doing is fine tuning for things like SciBERT, BioBERT, clinical BERT, to give like recognition of natural language processing from doctors' notes. is the specialization we were working in the medical school. Obviously, computer vision, another big thing, another thing that we can use neural networks for. If we think of an image as a set of matrix, an image has a set of values, and we could predict what that image is. So this has been around a while, and neural networks. So what you do is you take an untrained neural network, you have a training data set. So you say, this is a cat. You give it loads of pictures of cats. It learns what a cat is. Then you take that and you put a new image in and say, does this match your representation of a cat? And my favorite thing on the training courses that we run is finding pictures of Louis, because I love that dog. I could get a dog like that. I really do love that dog. So if you want to learn how to do that, Jenny and James, my colleagues, run training courses this month and next month to be able to train and run neural networks for computer vision and neural networks for this. So if you wanted to learn how to do that, myself, Jenny, James are all people who can help you do that. Obviously, that basic neural network, we can go further. We can not just find cats or dogs, we can classify it and find birds and things like that. One of the things I like about this image classification is if you take screen grabs of each layer in the network, you kind of think of how the computer's squinting to see things. You have a high level image, you have this thing and you're like, what's that? And then it kind of zooms out and you see the higher level. So as you go through the convolution, each filter layer, you can see what it actually becomes when it sees a person or sees the higher level features. So I kind of like thinking of these neural networks as different levels of squinting to see things. And you can then obviously use that to segment image, detect images like cars, and is a big thing of vehicle detection. But we can do things like find chairs, bins. And this is done through fully connected neural networks. So FCN8, FCN16, 32, and we can pick out people on horses, separate horses, cats and dogs. I myself was involved in a project, again in the medical school, because that's where I'm from, using ultrasound images for detecting aorta movements in the heart. And this uses the same fully connected neural networks. So FCN8 to detect a heart. And this is a UNet and FCN8 connecting together to find aorta in ultrasound images. And that we can train you how to do that. If you want to learn how to do that, we do coaches and courses for that. Another course we've done is for functional genomics. So we run this primer on functional genomics. It's in Jupyter Notebooks, and it's to predict whether proteins bind for a certain DNA sequence. And as you can see, they're positive or negative, excuse me, a positive or negative is the result of the assay. It's the dependent variable for that. At the moment, there are three main genomics deep learning tools: DeepBind, DeepSeq, and BaseSet are all used. And here we've created really a toy neural network just to do something similar to show how we could start. So this is an 8-level neural network we created just to find out whether that protein can bind. So it goes through the standard stages as you would in a neural network. You curate the data, you select your architecture, you have some way of evaluating whether that is a good result after it goes through your architecture, and then you interpret the result. I liked doing this primer, running this primer, because it actually has what they call the confusion matrix at the end to tell you how good their result was. So in the top left corner, we can see the confusion matrix, which is how good it was at predicting the result. And the actual a fuller way of testing the result would be doing the saliency map. and that's the silencing rabbit. It should only be the green, but obviously our 8-level neural network isn't perfect yet, but it does give some mainly the green results. So that is a whirlwind tour of what we can do, and some of the things Jenny, James, and Gavin can help you do in Baskerville. So if you have any questions or would like us to come and help you do this, we'd love playing with these toys. I really do.
Are there any questions for Simon?
Okay.
Oh, you
Oh.
we have the.
Oh, yeah.
Okay.
Excuse me.
Hello. Thank you both speakers for the interesting talk. I have two questions. So the first one is, I often run into like numerical issues with like mathematical models where we have to deal with a large magnitude of differences in the values.
Yeah.
So I was wondering if GPU is better at handling like all these numerical issues. I have I have a second question. So the second question is more like a general question. So we know that like with GPU we have improved in speed. At what cost are we running it? Is it more user friendly? Not user friendly, and energy efficient in terms of eco-friendliness? Is it better? Is there a study on that kind of?
Okay.
So you've got to remember both questions now.
But to answer the last question first, because it's like freshest in my mind. In both the slides for the Intel processor, 250 watts output, and the NVIDIA has 300. We're not plugging these into Raspberry Pis. They're massively power hungry, all of them. Even under LERD, they will. If you've been to the data center, they need water cooling. All of them need water cooling. Just the minute they become into LERD. Yeah, I mean, running this data set, I did a trial the other day, and within seconds, it had gone from 40 degrees, which is the standard temperature we were on the water cooling at, to 80 within seconds. When the minute I began running my application, I could see it. So yes, they're not eco-friendly, no. We are working on like the eco-friendliness of the system, but you are going to use power no matter what. And in terms of the variability of data, yes, it is a challenge in any scientific programming. You know, your level of precision is difficult to. I mean, how good enough is good enough? How close? I mean, for me, this is the point of the texture units, the tensor cores. They have that new B flirt, which is a half value of a flirt, so it doesn't have the full range of a flirt. And for neural networks, that's good enough, and it's close enough. But how close is close enough? It is the programming problem. If you're doing scientific calculations, sometimes you need the extra precision. But you've got to realize your edge cases. It's where you begin doing that. Yes, having that. I call it a fuzzy bit of logic in your code. You have to begin defensively programming fuzzily. It's like, is it 0? Is it close to 0? Is it close enough to 0? I mean, you have my problem with the saliency map at the end. But those will have been close to 0. The blue bits for the tensor cores, they will have just been edge cases that it only just, but some edge cases can be propagated to the system, and it gives a false positive at the end. So it is how good is good enough. So the 32-bit, I could have run it on the 32-bit integer system, and then I would have just got that. But would I have missed some potential parts of the system? Yeah. If that helps. It is difficult to clamp between, especially if you're talking about flirts, clamping 2 flirts, getting close enough is, I was once when I first started, I was involved in a machine that was digging trenches in deep sea. And they had this brilliant simulation on the seafloor. They wanted to pick up the robot and drop it on the deck of the ship. And it was great. It worked loads of times. It was great until you simulated sea, because you had one little bit of sea disturbance for the ship, and the robot would start vibrating on the deck. Like, but it doesn't vibrate. I was like, we all know it doesn't vibrate, but it goes through the texture slightly, and it starts vibrating like this. It's like, it's a 4-ton machine. We know it's not going to do that, but the mathematical model still says it's gone through. So then it begins reacting to that little precision inaccuracy. Any?
Thanks for the nice talk. So my question is like, mainly GPUs are kind of used in, like, as you showed as well, like on machine learning or neural network kind of calculations. So how good are GPUs for say finite element method type of calculations?
Well, okay.
And the next question I have is like, if I'm to build my own say finite element code, then can I get some help from their team on using these GPUs for such a calculation? Thanks.
Well, yes. I know I talked a lot about neural networks because, you know, AI is a big topic. It's hot trends, but, you know, GROMACS, LAMPS, they have finite elements, don't they? This is where they optimized it. It's a matrix multiplication. At the base of it, all it's doing is these calculations. You know, it has a massive parallel machine where you can load a matrix that is that big and do linear algebra. It is linear algebra all the way through, isn't it? Basically. Was there another question? Oh yes, building your own. Yes, we can help you do that. Like I said, I've had mixed results when I tried to optimize things through the GPU. So I can know where, but yes, we can help you program things. I'll introduce you to the CUDA core, the introduction to CUDA course we run, and the introduction to multi-node CUDA. We can begin showing you how to do that, and then we can build from there. So if you wanted to learn how to do CUDA first, then we can move on to doing more of the matrices. It'll be like a progression, and you'll be able to see it better than us, especially doing specific knowledge. It's like when I was working in the medical school with these people or doing the saliency things. I'm not an expert in biology. I come from physics. I did lots of radiation physics, but you know, I'm not an expert in that. I'm not an expert in natural language processing, but I know I took neural networks, I know artificial intelligence, and I know graphics programming. So I can help you utilize those. But domain specific knowledge, it's like at the end, there was some of that deep sea neural networks. They're doing genome predictions. They were like, at the end, they have how valid is this? You know, your P result is less than 0.5, so it's valid. But that's not true for genomics. If your P result is 0.5, it's like, well, that's massive. It's like the standard things in, you know, statistics don't apply in certain fields, you know. So domain specific knowledge, you probably have to help us with. And it's always interesting to learn other people's research. For me, I'm like, oh, how do they do that? So, you know, it's good.
Any other questions? Simon or anybody about Baskerville stuff? Thanks, Simon. Can you see that now? Right, so finally managed it. We can work Baskerville. We know how to do supercomputers. Can't share a PowerPoint presentation. So that's our next lesson, is to learn how to do that. So just to finish, so thank you to Gavin and Simon for those fascinating presentations. I think I've definitely learned a lot about Baskerville and just the sheer power of it and what it's capable of doing. So as they said, if you're interested in using Baskerville, then do get in touch with us. There's capacity in the system, as we've seen there, so we do want more people to use it, so, and we can help you to do it as well, so do get in touch and we'd be happy to discuss that with you. Just to flag up that our next session is on the 19th of July, and that's in this building, Alan Walters in G11, and that's going to be a cookies and code workshop. I'm hoping there are going to be actual real cookies involved, otherwise I'm not going. So I think we've been sort of promised that. So yeah, so that's one where you can bring your queries, questions. So if you've been trying to do something on Baskerville, trying to do something on Bear, and you've had a problem, or it's not as fast as you think it should be, or something, you know, just doesn't work, and you're tearing your hair out and you're stuck and you're wasting lots of time, then we have experts in the team and they're there to help you to do that. So do come along to the cookies and code session and we'll be happy to help you. One final thing before we wrap up is we have out at the moment our IT needs of active research survey, and we're looking for as many researchers as possible to fill this in. So whether you're a current Bear user or not, we want to know, are we doing things well? What could we improve, that sort of thing. So the closing date has just been extended to Thursday, the 30th of June. So you've got a bit more time to do it now. So we want to hear from all of you as researchers. So do let us know, do give us your feedback, and then we can act on that to improve Bear services and IT services moving forward. So that would be really helpful to us. And it's your chance to sort of give us your thoughts on how we're doing. So I think we're all done. I'll leave it up there for a few more seconds. So yeah, we'll end there. So thank you all for coming. I hope you found that useful, and do think about how you might use Baskerville in the future. And hopefully we'll see you at the next session. Thank you.